next class I'll review more of like do a little more practice for like the paired essay for next week. Really, especially if you could understand 29.2 and then like the practice diffusion and the hypotonic, hypertonic, there'll be some questions like that on it, as well as like some data analysis like we did in the last paired essay. But I'll show you some more examples like that next class. All right, so as I said, I moved 29.2 up in your reading guide. And basically 29.2 looks at, well, if you read the whole chapter, the first part of it was not super, it was kind of really getting into some of the details of plants, and then the second half of 29.2 is really where we get into the water potential stuff and the relevant thing for AP Bio. And yeah, so basically we're looking at in 29.2, how does water move in plant cells? And so basic definition of osmosis, already gone over that. Water potential, it's related to this idea of osmosis, but what can happen with plant cells, because plant cells have that cell wall, plant cells basically can have like actual pressure that happens. And I'll explain a little bit more what I mean by that when I can show you some examples, but basically water potential, it's looking at how does the amount of solute, the solute concentration, and the pressure, so that pressure that's coming from like the environment that plant cell's in, how does that change which direction water moves from? And this is key. This second bullet point, you have to understand this. You got to memorize this. Otherwise, you'll get lost with these problems. So you got to memorize water wants to go from high, let's do this, let's do like an arrow, like high water potential. So water goes from high water potential down to low water potential. What is potential energy? Somebody explain that to me. Give me an example or something. Go ahead, Aditya.
It's energy that's like present, but you're not using it at the moment. So like, if you honestly,
Yeah.
if you rather be like not really using energy, but like in the 10th of a second, all that energy.
Yeah, it's like stored energy. Yeah, so your swing example, when you're at the top of that like loop, I don't know what you call it. That's like highest potential energy, and then it goes from potential energy and it gets transferred to kinetic energy. Okay, so to understand water potential, get that, you have to understand potential energy. Get that idea in your head. So I'm holding my sock up here. This would be the highest amount of potential energy, and then as I drop it, it goes from high potential energy down to lower potential energy. So higher water potential, water wants to go from the high water potential down to the lower water potential. So this is the movement of water. Okay? Meaning you might think in your head water would want to go from lower water potential to higher potential, but it always wants to go from higher water potential to lower water potential. In other words, it's the potential for water to move. Potential energy is the potential for this sock to move down. It isn't moving, the water isn't moving yet, but it's the potential for it to move. Okay? All right. How we abbreviate water potential is with this like pitchfork looking symbol that we call psi. I kind of think it's amazing. Like, let's just draw like a pitchfork. And the actual unit of psi is megapascal. So MPa is what we'll call it. Where if you're at pure water at sea level, we say you are 0 MPa. I'll show you a formula in a second here. You'll get this formula on the AP exam. Fortunately, you don't have to memorize it. But this is a very common test question. Like, if you have water, if you have something at pure water at sea level, what is its water potential? And that is 0. And when I get into like what makes up water potential, it'll make a little more sense why it's 0. So yeah, looking at this formula, water potential, the pitchfork, psi, equals the solute potential plus the pressure potential. So going back to that pure water, how much solute is in pure water? 0. Pure water is just all H2O. There's no sugar or minerals in it. That's why pure water would have a solute potential of 0. If you are at sea level, what's the air pressure there? The pressure, the atmospheric pressure, be 0. So 0 plus 0 is 0. That's why pure water at sea level and at room temperature, I'll show you how room temperature factors into this a little bit later, is 0 MPa. Okay. Solute potential, we also call that the osmotic potential. And because that's going to be like the solute potential is one of the biggest things that's going to cause the water to move into or out of the cell, especially in some of these practice problems. Where the pressure potential comes into play is like, you know, if I were to like have you know, say you had like your dialysis bags or like you have a cell and that cell is in like a beaker of water. So here's my cell, here's a beaker of water. If I'm able to like squeeze this container closed, I shorten the volume, that's going to want to force water to go into the cell, right? By like shortening the volume of the container, you're increasing the pressure that this cell is going to feel, and that's going to then drive the water into the cell. So it's kind of common sense, but if you increase the pressure, that's going to increase the water potential. The water is going to want to move on into the cell. Okay? All right. Getting into some of like vocabulary you see around this, and then I'll show you some practice problems with water potential. There is Turgor pressure, which I mentioned before when I said like if you put a plant cell in a hypotonic solution, the water wants to move into that plant cell. That plant cell, the central vacuole, is going to absorb a bunch of water, and we say that plant is turgor, meaning the water. If I draw my plant cell, here's your giant vacuole. You know, the water is pushing. That expanded vacuole is going to push on the cell wall, and the cell wall pushes back, and that gives that plant some structure. So that's Turgor pressure. The amount of pressure that cell would feel is the Turgor pressure. The protoplast, it's kind of a more random vocabulary word, but basically the protoplast is referring to everything in the plant cell but the cell wall. So they call it the living part of the cell. So basically the non-living part of a plant cell is the cell wall. Reason for that is like the cell wall isn't really like I guess changing as much, whereas everything else, like including the cell membrane and the plant cell, is constantly like undergoing different chemical reactions, whereas a cell wall is more or less just kind of stays there. You might add like the secondary cell wall as the plant matures, but it more or less is kind of staying constant. Yeah, I've talked about how that Turgor pressure is what gives plants kind of a lot of their structure. And also can play a role in cell elongation, so like how a plant can like slowly start to grow. And then, yeah, these last two bullet points really aren't as relevant for you. But what this is saying is, you may remember what the xylem does in a plant? From like freshman bio or 7th grade bio? I used to teach this teacher and say, xylem up, flow them down. What is the xylem going up with?
Oh, what's the water?
The water. I think of it as, you know, when you know your ABCs, you go W, X, Y, and Z. So like W for water, X, Y for xylem. Anyways, the xylem will carry the water. The reason why the water can go against gravity from the roots up the plant is at the top of the plant, water evaporates, like through transpiration, and that creates a negative pressure potential that draws the water up through the roots. Anyways, as I said, it's not really as relevant for like the Unit 2 tests and stuff, but there were just bullet points that existed on the pre-made PowerPoints. Okay, so this is just saying what I've already said. Water potential goes from higher water potential down to lower water potential. So let's get into some examples of I'll come back to that. Let me show you a little more concretely what I'm talking about with some examples. So we have our initial flaccid cell. Remember, flaccid means the cell isn't full of water. So this would be a cell that was in like an isotonic solution. it doesn't have the maximum amount of water inside that central vacuole here. So we would say here, they would give you the pressure here. They're telling us here that the pressure this cell is feeling is 0, okay? And the solute potential is negative 0.7. Now, solute potential will always be negative. Like if I add solute, we always say that that's going to cause a decrease in the water potential. So let me write that down for you. So adding solute lowers the solute potential, the pitchfork sub S. Any thoughts, like based on this right here, why that would be so? Why would adding solute lower your water potential? So if I have a higher water potential, this means I have more solute. Wait, I'm sorry. If I add solute, I have more solute. More solute goes with a lower water potential. Because remember, water wants to go from where there's less solute to where there's more solute. Right, or looking over here, it wants to go from hypotonic, less solute, down to hypertonic where there's more solute. In other words, see the connection between hypotonic, hypertonic, and water potential, high and low. High water potential is less solute, which is hypotonic. And lower water potential is more solute, which is hypertonic. This is why in the Mastering Bio I gave you a lot of practice with this, because it's very easy to start like mixing this up in your head. This is kind of like your North Star that you got to keep straight in your head. Otherwise, especially like on a test and stuff, and your self-confidence starts to waning a little bit, it's easy to mix this up in your head. Getting into this example here, my flaccid cell, I have negative 0.7 MPa. That's my amount of solute. I put it into a sucrose solution that's 0.4 molar. And they're telling us that the sucrose solution here is lower. I have lower solute, meaning I have more solute outside of that cell. And that's why the water is going to leave. If you have more solute, we said more solute means you are hypertonic. This solution is hypertonic, and inside the cell is hypotonic. Make sure this makes sense to you. The water is going to leave. It's going to go from higher water potential inside the cell. This was higher water potential to outside the cell, which is lower water potential because it has more solute. Okay? All right, and then it'll keep doing that until we get to equilibrium, until the final plasmolized cell is going to have the same. It's going to have the same water potential as the surrounding environment. Things will equalize. Okay. All right. Then let's do another scenario. Let's say you take that same flaccid cell, that same solute potential, but now you're going to put it in pure water. So pure water now has less solute now. So now our environment has less solute, or it is hypotonic. And that's why the water is then going to move into the cell, because if the beaker is less solute and hypotonic, inside the cell here is going to initially going to be hypertonic and have more solute. Remember, more solute means you have a lower solute potential. Initially, this cell, because it's at a negative 0.7, that means it has more. It's backwards, is what I'm trying to get at. More solute is a negative number. It's a negative number because that's going to cause a decrease in your water potential. Lower water potential means that's where the water's going, like the higher to lower. Okay? When I'm done going over the notes, if you're confused by that, like you got to make sure you're not going to be able to memorize some of these practice problems until this can make sense to you a few different times. Okay? All right. I'll keep it moving. Purpose of this picture is try to get you to understand the pressure where does the pressure come from in that formula? And let me write the formula down so you have it for reference. So water potential, or psi pitchfork, is solute potential plus the pressure. So here, here's pure water. Let's say I put a bunch of solute to the right of this membrane. Well, now this is hypertonic, right? I have more solute, so the water would like to go from left to right. But let's say I have another scenario. Let's say I have my pure water, and I add pressure to the left side. Well, now this is going to be higher pressure. The water is going to move over to the right. Or if I do negative pressure, this is kind of how like your lungs work. I don't know if you knew that. Like, what causes your lungs to expand? Like, you don't suck in air. You ever thought about that? Like, what makes air come into your lungs? It's not like you like using energy to like suck in the air, like you're Kirby or something. Like you expand yourself, you expand your lungs. When you breathe in, you expand your chest cavity, and then that creates negative pressure, which then causes your lungs to expand, to fill the space. Anyways, so there you go. All right, a little bit like, let's see. Yeah, having solutes, more solutes will lower your water potential. And then, yeah, this is just saying you put a flaccid cell in pure water, it becomes more firm. It becomes turgid, the water is going to move in. Okay, so kind of stuff I've already said so far. Yeah, so basically it's like in a plant. Like this is wilted. So these plant cells would be not turgid. So these would be plants where like inside the plant, those plant cells would be hypertonic, right? They don't have enough water. And then these plants would be, oh, they're nice and turgid. These plant cells have gotten all their water. You put them in a hypotonic environment and the water went into the cells and they're nice and firm. Yeah, I don't know why they have the same picture there, but. Okay, so something else we got to talk about with the water potential calculations is how you can calculate the solute potential given your concentration. So these formulas you don't memorize, are given to you on the AP exam. I'm going to write this one below. So psi solute potential is negative I CRT, where I is the ionization constant. So if you have salt, the ionization constant is 2. Anybody know why that would be? NaCl would have an I of 2. Any thoughts on that? So salt is NaCl. We would call that an ionic compound. Na is +1, Cl is -1. You put that in water, it splits up into 2 separate ions. That's why it has an ionization constant of 2. Whereas glucose or sucrose, your sugars, they aren't ionic compounds, they're covalent compounds. They don't break apart into multiple ions. That's why when you put them in water, they have just a 1 for the ionization constant. Okay, so usually 1 or 2 would be your number for I. Aditya? Yes, yeah. Basically, yeah. How many parts does this break up into? NaCl breaks up into 2 parts. Glucose, when you put it in water, glucose breaks apart into it doesn't break apart. It just stays as 1. Okay? All right, molar concentration. This is in molarity. So molarity is moles per liter. So this would be something that could be either given to you or, and this is getting into your paired essay for next week, learning how to interpret a graph where wherever the line crosses 0 on the graph, that would be we would say that's the molar concentration. I'll show you an example of how you interpret that. It's not super complicated. It sounds kind of goofy when you just see it on words right here, but if I show you a graph, it'll make some sense. Then the pressure, we call that pressure constant. So unless they tell you otherwise, you can assume it's this number. And this is given to you on the formula sheet. You don't have to memorize 0.0831. Temperature, if they give it into degrees Celsius, I don't know if you learned this in like honors chem. If you took non-honors chem, we didn't go over this, but to go from Celsius to Kelvin, you add 273. So let's say room temperature is about 23 degrees Celsius. To get that into Kelvin, because this formula is in Kelvin, this pressure constant is in Kelvin, you would have to add 273 to whatever your degrees Celsius is. You with me here? Okay. Don't have to memorize this formula, just knowing how to use it. All right, this is showing you what I was mentioning with like the point at which the line crosses the zero. That's how you find the molar concentration. So you're going to see something like that's like this, very similar on your paired essay, where I'll give you a graph, and this is showing percent change in mass of potato cores in various sucrose solutions. Basically, this is like what you did with your dialysis bags, but instead of potato cores, you had dialysis bags, where you had we had different concentrations of sucrose solutions, and the mass change, you went from if you had a positive increase in mass change, you were 20. If you had a loss in mass, you would have a negative percent change in mass. Right here, where we cross the x-axis, this is where you had no net change in the percent mass change. In other words, no net movement of water. So think about what that's saying. If I have no net movement of water, let me draw like a sample cell. So here's a cell, and let's say I have 4 solutes inside the cell and 4 solutes outside the cell. We would say this is isotonic right here. There's no net movement of water. So then water goes in and it goes out at the same rate. So you would have no change in mass. Meaning, wherever this happened at, wherever you meet on the x-axis here, x-axis being the molarity of the sucrose solution, let's say that's like 0.35, that's going to tell you that is the concentration of sugar inside those potato cores. So, in other words, that is going to be my C. 0.35 would be my C if I'm trying to calculate the solute potential inside those potato cores. Does that make it? Like, that's got to make sense to you. Wherever it crosses over, because that tells you it's isotonic. Now water's going in and out at the same rate. Okay. All right. I think I've said everything here. Let me read it real quick. Oh, I haven't. Yeah, if you're in pure water, well, I didn't mention this. Pure water, solute potential is 0 because there's no solute. Remember, as you add solute, the number gets more negative. This solute thing will get more negative. And as you see what makes solute potential, the formula for it, that should make sense to you. If I start making my C higher, I start increasing the concentration of my solute, that is going to make, there's a negative here, that makes this negative number be even more negative. Seeing that? You make that, you increase your concentration, you get a higher negative number, which then would give you, like, more solute gives you a more negative osmotic or solute potential. So there you go. Okay, so what might a practice problem look like? And in Mastering Bio, there's some pretty good ones to kind of see what these look like. But they're telling us the molar concentration of a sugar solution in an open beaker. What would that tell you? Open beaker, classic test problem. What would that tell you looking at the water potential formula? What might that tell you? If you were an open beaker, what would that, yeah, it has to do with the pressure. What would that tell you about the pressure? How much pressure something would feel if it's a completely open container? Think of evaporation. Like if you have nothing holding those water molecules down, they evaporate very easily. Yeah, it's 0. So the pressure potential is 0 in an open beaker. Okay? All right, so I'm telling you molar concentration is 0.3 molar. That's my C. Okay, Okay, that's the C in the solute potential calculation. And then we're at 27 degrees Celsius. You have to get that into Kelvin. How would you get that into Kelvin? Yeah, add 273. So my solute potential would be negative I. Well, what is my I here? If I'm working with sugar, how many parts does sugar break up into when you put in water? Just one. Because it's not ionic. It's not going to break apart into multiple. Just be one. Now, if I said this was NaCl, this I here, that would be 2. Okay? And then C, they give you C, 0.3 molar. So they're either going to give you C. I mean, they're not going to like make you do stoichiometry problems and stuff and like give you atoms and like it's not going to be. What they may give you though is like a graph like this where you got to look at where it crosses the x-axis and go down to the molarity on there. Okay. Anyways, they were nice and just gave you the number 0.3, and then R. That's a constant that I don't have memorized. 0.0831. So this is times 0.0831. And then times our temperature. So 273 plus 27 is 300? Yeah, 300. And that equals this number here. Negative 7.479, and we say bars. You know, like we're a bunch of rappers spitting bars, you know? So this number would equal negative 7.479 bars of solute. So that gives you your solute potential. Then you could put that into the overall water potential. So for that problem, if it's in the open beaker, the water potential will be the same as the solute potential because we said for that problem, the pressure potential was 0. Okay? All right, so that's the end of the notes for it. As I said, go on Mastering Bio and try doing some practice. I also, in the quizzes on the first slide, I have some practice problems you can do. Yeah, there's only so much hearing me talk will, I think, help you with this. Just try doing these samples, and I'll help you out with it. Here, let me pause the recording, or stop it, and I'll come over there.